Welcome to another week of distance learning in physics class. We are getting very close to circuits, which is very exciting. But before we can really dive in, we need to go over a very fundamental part of theory for electricity, and that is electric potential. So electric potential deals with the energy of electricity and how we can harness it to do useful work. And I want to frame the context of useful work for electricity in terms of what we have already learned. Previously, we have thought about work in terms of mechanical energy. So we've looked at kinetic and potential and how we can flippy-floppy between those two forms of energy. So let's jog your memory of how we like to think of energy and how we can use it to perform useful work. Previously in class, we've explored how energy can take on so many different types of forms, right? So we can think about sunlight and how trees and other plants harness that form of energy and turn it into another form of useful energy, like chemical potential energy in food, right? How do we go from more classical physical examples of energy to electricity? We can think of this energy in so many different types of forms. And what we've learned about in class has primarily focused on the more classical physical examples of energy. So right now, you can see that I have a lot of gravitational potential energy, pretty high up. But how do we think of that conversion between potential energy and kinetic energy in terms of the potential energy of batteries to light up a light bulb? We've talked a lot about the electric fields and how charges move in these electric fields around charged objects. Let's start making the connections between how potential energy, like in these batteries, reflects to these classical physics ideas that we've already learned. So, let's pretend these batteries with potential energy, let's say they're represented by this kettlebell. So we're high up off the ground. We've got a lot of potential energy. Let's think about this kettlebell as a lot of electrons on one side of a battery, right? So we've got a lot of potential energy, Oh, this is heavy. And we can drop it. We can let that current flow, right? To do useful work. I want you to start thinking about how this kettlebell that started with potential energy and ended up switching all of it to kinetic energy, how we can think about that in terms of batteries and what we're going to learn about electric potential. Hello friends, welcome to another week of physics class. This week we will be focusing on the idea of electric potential. This directly builds off the idea of an electric field, and this is a super duper important concept in order for us to actually move on to, how circuits work, how does electricity work. I do want to note that this topic is pretty tough to kind of digest. I do actually recommend that you go grab some paper, grab a pen, grab a pencil, and take notes as you go along with me. The first thing I want to talk about for electric potential is a really big key idea that links together types of energies. So this is the key idea. Both electric and gravitational Gravitational forces can store mechanical energy as potential energy. This is a super duper important concept. We've talked about gravitational potential energy in depth before, right? So, in the demo, I dropped a kettlebell off of the top of a high ledge. We've looked at tennis balls, how that mechanical energy flip-flops between kinetic and potential. Let's start kind of linking those ideas to electricity. We know that in the more classical sense of potential energy, so gravitational potential energy, as we lift an object higher and higher above our reference point, so as that height increases, our potential energy due to gravity also increases. I want you to make the parallel that electric potential energy behaves in a similar. Let's say that we have a negative charge here. So you can kind of pretend like, oh, this kind of planet, this Earth is kind of like a giant negative charge, right? So as you bring this positive charge farther and farther away, so as we increase the distance, the electrical potential energy also increases. So one of the classic examples for this is to think about this positive and negative charge like it's separated by a spring, right? So we know that opposite charges attract. So we're going to have to put in energy to peel those charges apart, right? And we can store that energy we put into that system, right? So that spring, the spring between the positive and negative charge wants to snap back together. We say that we're increasing the potential energy of the system. You might be wondering at this point, okay, well, where in the actual system between the charges, where do we put this energy? The answer is that electric fields store mechanical energy. So we talked about last week how important these electric fields are, right? They really help define how the energy flows in an electrical system. And that's why we looked at it so much. You got to understand the fundamentals before we can build up. Again, let's go back to that example of the spring. Let's say that I am holding a positive and a negative charge. Let me color those in. Positive and negative apart, right? So for me to pull those charges apart, it's going to take work to pull them apart, right? Conversely, let's say, ooh, that's a really bad person. I got a really long torso. Let's say, conversely, I have two like charges. Let's say I have two positive charges. I'm also going to have to input energy, input work to squish them together, right? Because opposite like charges repel. So again, I'm going to have to put in energy to squish these together. I'm going to have to put in energy to push these apart, right? And again, we can store that energy inside the system as potential energy. So again, just to reiterate, this energy that I put into the system is stored as electric, there we go, electric potential energy. Ah, I told you all that energy always ends up coming back, right? Again, we are in a physics class and we like to be quantitative, although it's good to be able to describe things qualitatively too. So let's think about how to measure these values, measure these energies, okay? So we know from the past, when we've looked at, converting energies, we can look at work, right? Work as kind of a form of how to use that energy. So we say that the work done by an electric force is defined as the following equation. The work is equal to the negative value of the charge, Q. So I'm going to put this little line through it to indicate that this is a Q, okay? Times the electric field times the distance, okay? Let me write out all those variables so that you have a reference point, okay? So W is work, and we know that we think of work in terms of joules, so that's joules. Q, the charge. We've looked at this. It's in coulombs. The electric field, E, is newtons per coulomb. And then finally, D is just distance. And we think of this in terms of meters. This equation should make sense when you start to think about it, right? So think about how we've looked at charges interacting together, right? So again, let's say we have a positive charge and we have a negative charge. If I want to draw the electric field lines, we know that they should point, hopefully you're filling this in your head, sorry if you heard my dog yawn, which direction should they point from? Should they go from the positive to the negative or the negative to the positive? Hopefully you said positive to the negative. This is the convention for electric field lines. Okay, let's think about if we're trying to, shuffle these charges around. Like, do we have to put in work? Do we not have to put in work? Are we kind of compressing that spring? Are we stretching that spring between them? And so this equation should make sense, right? So it depends upon the actual value of the charge, right? Is it a big charge? Is it a little charge? It depends upon this electric field between the charges. So we looked at that for the past few weeks. And it also depends upon the distance between the charges. Think back to Coulomb's law and how, that force of attraction or repulsion depended upon the distance. So really what we've done here is all the past few weeks of what we've studied, we've now combined it all to think about energy. I want to go one step farther for this equation. And again, I do recommend that you actually are writing these down because otherwise I feel like it's just not going to stick in your head, okay? So we know from the work energy theorem, haha, stuff from class way back when is coming back. We know from the work energy theorem that we can define work as the change in kinetic energy. So remember all those examples of me pushing, my dog, that's Willow. Willow in a box, right? I'm pushing Willow. So I'm putting in work, I'm putting in a force, I'm putting in work, and Willow is gaining kinetic energy as I push her, right? I was going to do a demo with that for this video, but I couldn't get my dog in the basket. So we can think of work as change in kinetic energy. But we know that kinetic energy is directly related, well, inversely related to potential energy, right? So, think about that tennis ball. As that tennis ball goes up, we gain potential energy. And as that tennis ball comes down, we lose potential energy. But again, when we lose that potential energy and that ball's falling to the ground, we increase kinetic energy, right? And vice versa. So I am going to rewrite this work equation in terms of potential energy. So we know that as kinetic energy goes up, potential energy goes down for these classic physics examples like the ball. So I can say that work is also equal to the negative change in potential energy, right? So this is the same thing as saying the positive change in kinetic energy. Okay. Let's start linking together even more ideas, right? So I just told you this, that work is equal to the negative change in potential energy. And we also just talked about how for electric systems like charges, we know that work is equal to the negative charge times the electric field times the distance. Let's start swapping stuff out in equations. So I can say that the work here, I'm going to swap that in here. Now we're directly relating the potential energy of an electric system to the work. When I do this, the equation I get is negative potential energy change is equal to negative QED. Again, all I did was swap this half of the equation of work for this one. Okay, I can cancel out that negative sign, and what I end up with is the change in potential energy is equal to the charge times the electric field times the distance. Haha, we have now linked together the fundamental idea of how energy changes in an electrical system. Before you can move on to the first couple of problems in your weekly assignment, we need to define a new idea given our new knowledge about energy and electricity. And you could probably guess where I'm probably going with this, because I know all of you have heard, voltage, or, this battery has a certain number of volts, right? So let's start thinking about what voltage is. Voltage, change colors. Voltage is the electrical potential energy per charge. So we've looked at how we can define the actual energy, but how is that useful to us? How do we as people use this information in a useful way to power the stuff we need to power with electricity? And that's where voltage comes in. So we're taking that energy value and saying, okay, I have this amount of energy, but what work can I do with it? I want to put this in terms of an equation because, again, physics, quantitative, right? So what I'm going to say is the change in electrical potential is equal to the change in potential energy over the charge. Okay? What this means is that as we change the potential energy of the system, so think of that tennis ball going up and down, right? Or think about those electrons going around a circuit. That change in energy per charge gives us our voltage. So voltage is the change in electrical potential. And we're going to go over some more examples later on to help make this more concrete. Again, I know that a lot of this is kind of abstract feeling, so let it sit in your brain, let it settle, and we'll move on and do more application bases for this. Before I forget though, units are very important. So the unit for electric potential is the volt, so V, and this is equal to, let's see if we can dissect this equation to figure out those units, what it means. Potential energy. What is our unit for energy? Hopefully you said the joule. And what is our unit for a charge? Hopefully you said C, the coulomb. So a volt is equal to a joule per coulomb. And again, I get it. This is kind of abstract right now, yeah? But when we start to actually get into the pieces of how electronics work, it's going to start to make more sense. Before we move on to the first couple problems in the assignment, I want to show you a picture to help you visualize what's going on. Okay, so is that in focus? Let's make that in focus. There we go, great. Okay, so the first thing we talked about was that key idea linking gravitational potential energy and electric potential energy. So let's say that's some pink hair. Let's say I have a ball in my hand and, I have it at a certain height here and I lower it closer to the ground, right? We understand, we can describe like through numbers how the energy, the gravitational potential energy is changing in this situation. Let's try to visualize the electric version of this, okay? So we have electric line fields here, which you can, in this analogy, it's kind of like saying like, okay, the height of a person off the ground, right? So we have this energy inside this field, and this little charge is going to travel. It's going to travel a certain distance in the electric field. As it travels a certain distance in the electric field, its energy is going to change. Yeah? So hopefully you're linking together kind of the macroscopic and the microscopic, okay? Next, we're going to link the previous section's ideas to, honestly, this is kind of a hard concept. Again, if this doesn't make sense right now, maybe, go take a walk, go take a break, and then come back and revisit. What we're going to do now is link together how the electric potential, so that energy, how that relates to the electric field. I told you previously that the electric field kind of like contains that energy, right? So let's explore that. First, I'm going to give you an equation, and then we're going to dissect it. So the electric field is equal to the negative change in the electric potential, so the energy change, over the distance. And when I rewrite that with variables, I have E for the electric field. I have that same negative sign. Electric potential is the voltage. Change in electric potential is the voltage. Yep. Over distance d. Yeah. The units for this are I can't spell, volts per meter, or V over M. Before we plug in actual values to explore this idea, let's think about this conceptually, yeah? Let's compare two scenarios. Let's say sorry, intense drawing. Let's say we have two positive charges that are very close together, right? So we're having to compress that spring, put in work to push them together. Let's then consider scenario 1, scenario 2. Let's consider two positive charges that are farther apart. I want you to rank which scenario, 1 or 2, has the higher electric potential. Remember, the electric potential is related to the energy of the system. So, related to the energy, and energy is related to the work, right? So, which scenario, 1 or 2, do you think it takes more work to push them to that distance? So in number 1, we push them two positive charges like together, but in number 2, they're kind of chilling apart. Thinking of that, think about how much energy it takes to get these charges to these final positions. So, which scenario, 1 or 2, has the higher electric potential? That would be number 1. Again, you're putting two like charges together. That takes energy to do that, right? So let's look at a cartoon from the book showing the same exact thing. It just looks a little neater. So on our y-axis, we have electric potential or voltage, and we're comparing the electric potential. So like charges close together produce a high voltage because they store a lot of energy, right? Y'all knew that. Let's link this idea of the electric potential to the electric field, though, right? So we're synthesizing all these ideas together. In this diagram, in this picture, we have an electric field, so it's traveling from left to right. So we can say that there's a positive charge on the left because the electric field is radiating outwards. So let's say we drop a little itty bitty charge, this little charge Q, in this electric field. Yeah? This charge is moving with the flow of the electric field. I like to think of these as kind of like, you jump in, or like a cute little river otter jumps into a current of the river, and it's going with the flow. It doesn't really have to input a whole lot of energy, right? It's going with the flow. So as the charge Q moves in with the electric field, the electric potential decreases. And again, this is how we define it mathematically. So the change in voltage is equal to the inverse of the electric field times the distance, right? So if you're going with the flow of the current, you're not putting in extra work. You're letting it do its thing, right? So in this case, again, my mind just always it goes with the flow. And additionally, the way my mind likes to think of increasing the electric potential, increasing the voltage, is that if you would have a hard time, like if you have to input energy to do the thing, then you're going to have a higher voltage. So again, if you have a positive and negative charge and you try to pull them apart, you're going to have to put in energy to do that. So you're going to have a higher electric potential. It's like conflict causes the voltage. That's how my brain thinks. So at this point, if you could work on the next section of problems and then come back when you're ready. The last thing I want to talk about for this week's lecture is how electric potential decreases with distance. This intuitively makes sense. If this is the Earth, and this is you, are on one side of the Earth, and your friend is on the other side of the Earth, and you're each holding an electron in your hand. You know those electrons are not going to sense each other. They're not going to have an interaction. They're too far apart. There's a certain optimal distance. And we've looked at this already, actually. Let's go back to a few weeks ago when we looked at Coulomb's law. Before I write the equation, I want you to think about what you remember about Coulomb's law. What was it about? Do you remember the equation? What hopefully is going on in your mind is that we know Coulomb's law deals with the force between charges. So the attraction, the repulsion, the force between them. And we maybe remember there was a constant in there, and that we looked at two charges, Q1 and Q2, over the square of the distance. And I asked y'all to tell me graphically how that force and that distance were related. We know that the force is proportional to, so this little fishy thing, it's called an alpha, is proportional to 1 over the square root of the distance. So if you actually plug numbers in here, you would see that as force increases, distance decreases, and vice versa. Which one did I say? As force decreases, yes, distance increases. Yes, there we go. And so the plot of this is an exponential decay, right? So we have the exponent here, it's a decay. Okay, so this was looking at the force between charges. And remember, from our unit on work, we can think about forces doing work, and then, work connects to energy. So can we connect these ideas to electric potential energy? Let's try that. So I have, if I can grab a sheet of paper here, I know that the electric potential is directly related to charge, and I can probably guess that it's inversely related to distance, right? So think of that example I just gave you where you and your friend are on opposite sides of the Earth. Do you think a battery is super useful if you're on opposite sides of the Earth? Probably not. I'm going to give you an equation here. I'm not going to derive it because I think that's a little bit too much for like an online lesson like this. If you're interested, reach out, ask me. But I can define that the electric potential is equal to K, that electric constant, times the charge over the distance. If you're curious how I got this, a few weeks ago we looked at electric fields and we kind of simplified an equation, and that's where this equation comes from. Okay, again, if you're interested, reach out. But otherwise, you're going to take my word for it that this is correct. And you can see that electric potential, so this is the voltage, is inversely proportional to the distance. And again, that makes sense. And in this case, again, so this unit, the unit, we're looking at volts, B. There's a problem in your packet where I want you to think about this, okay? So I give you the equation, but I want you to think about what this physically means. Before you finish off your packet, I do want to show a picture. Let's focus that. There you go. Okay. Because I know some people learn a little bit easier through some pictures sometimes. So right here we have a parallel plate capacitor. And I've used this as an example a few times now, and it's because parallel plate capacitors are really cool for explaining these concepts, just because how they are. So on one side of the plate, we have all positive charges. On the other side, we have all negative. And we know from the past few weeks that the electric field lines should point from positive to negative. So they go, oh, that was a really bad straight line. They go that way. And so let's say you drop a little charge, a little positive charge over here, right? So it's going to travel along that current, that stream, that electric field stream towards this side. And as it travels, our electric potential drops. Ah, that makes sense, right? We just looked at voltage versus the distance. So we're connecting ideas here. So next week, I'm actually hoping we can start to get into circuits. Yay! If there are any specific questions you have about circuits that you want to kind of address before we dive in, please feel free to reach out. I know I think this is a fun topic. Yeah, so now you are ready to finish the remainder of the packet. If you have any questions, reach out. I have office hours Wednesdays and Fridays from 3 to 4 p.m. at the standard meeting ID and password. Okay, I hope you have a great rest of the day, great rest of the week, and have a nice day, friends.